Good morning.
Good
Good
morning,
morning,
Professor.
Professor.
Uh, let's take a look at the schedule for the schedule here and notes. Okay, I'm going to start sharing the screen. We go to the 21st April. 2025, and we are almost done with chapter electromagnetic induction. Let me adjust it here first. The only thing that's left is the transformer. Syllabus. So what I'm going to do here, I'm going to put electromagnetic induction number 3, right? Chapter 22, one more student coming in. And our exam is going to be the day after tomorrow, chapters 20 and 21, labs 1 and 2. And let's take a look at the notes. This thing here, and another student. Insert page break. Let's see. 21st, 25. That's a Monday. Which week is this one? Week number 11. Week number 11, meeting number. Let's see. Meeting number 17. So all that's left today, let's see. By the way, I corrected your lab report, the report for lab 2, and uploaded to Canvas and uploaded your correction. Canvas. Okay, exam is the day after tomorrow. Chapters 20 and 21, labs 1 and 2. Chapters 20 and 21, labs 1 and 2. Exam 2, right? The day after tomorrow. Partial exam, let's be even more precise here, partial exam 2. More students coming in. And all you have for chat, we must We'll cover the last section of chapter 22, which is transformers, And we'll start chapter 23, AC circuits. And let's take a look how transformers, no? We have transformers all over the place, okay, especially in the streets. What are transformers, right? What are transformers? Okay, transformers are electrical devices that work, let's see, that can change voltages in a rather straightforward way, and in a rather straightforward and efficient way, using the law of induction. Okay, because it depends on the change of the magnetic field, right? It works only with AC circuits. Transformers do not work with DC circuits. Well, why is that? Why is that? Why is that? That is because the law of induction relies on the changing current. If a circuit does not change its current, then you cannot induce a current in another one, okay? And let's take a look in the internet. Transformers, okay? Transformers. No, I don't want the TV series, okay? Electrical transformers, that's what I want. Electrical transformers. You go. One more student here. Oh. Okay, here you go. We have a very good picture here of a transformer. Okay, so what you have here, you have one solenoid here on the left, and you have another solenoid here on the right. Okay, you already know. Let's go back to our drawing that I made. I showed to you before. Let's see, that's the one here. Yeah, that's the one. Recall this drawing that I made for you, right? We have a solenoid, a main solenoid that's powered by a generator, and you have a secondary solenoid that's inserted on the inside of the primary solenoid. What you see here is already a transformer. This thing works as a transformer as well. Okay, because why is that? Because this solenoid here is inducing a current on the secondary solenoid. Okay, So this guy that you see right in here, it does work as a transformer because the primary solenoid is inducing a current in this secondary solenoid. Okay? But we have a different way, a different geometrical configuration to do the same thing that we do right in here. That's the easiest way of understanding how a solenoid works, okay? And people discover that this configuration here is rather inconvenient, okay? Because you have to insert one solenoid inside the other one. But people discover a rather simpler way and very convenient way as well. Instead of inserting one solenoid in the other, what do? We get two coils, two solenoids, okay, or exactly the same size, not exactly the same turns, okay? And then we insert this metallic bar on the inside of both solenoids. We see we have this metallic bar here. It's not a metallic bar, but the metallic donut, okay? And what happens? Doing something like that is the same as inserting this solenoid inside the other one. It's exactly the same, gives exactly the same result, okay? And what's going to happen? The magnetic field that, for instance, the solenoid here generates is going to be concentrated inside this metal donut, okay? That's and now you can have two solenoids side by side. They can have exactly the same area. In the other case, you didn't have the same area. You had a different area. And to simplify your calculations, okay? And let's see if we can get another picture here. Here you go. Here's the symbol of the solenoids. The solenoid or the transformer. One solenoid, another solenoid, and here you go, the metal that connects the two solenoids. Let's see if we have another. Here you go. Here's a circuit with a transformer. See here, the generator right in here. This other circuit doesn't have any source whatsoever. The source of this circuit is going to be this other circuit right in here. And by electromagnetic induction, the current is induced, a current is induced in this part of the circuit. Okay, here you go. Here's I prefer this drawing. Okay? So here you go. We have the primary solenoid right in here. Okay, we don't show the generator, but we do have a generator right in here. See that? Primary current, primary voltage. That's the primary winding. 1, 2, 3, 4, 5. We have a bunch of turns here. And we have this metallic kind of a square donut, right? A square donut. And why do we use that again? Well, we use that to concentrate the magnetic field here in this region. Without this metal donut, the magnetic field is going to be the induced current in the other solenoid would be very weak unless the second solenoid would be inserted inside the first solenoid. Okay, but that's the practical way that we found out to create a transformer. And what's the advantage of the transformer? Okay, so it's just the transformer is used to either increase or decrease the voltage in the other circuit. Okay, by adjusting the number of turns, the relative number of turns between one solenoid and another, we can either increase the voltage or decrease the voltage. And there is a very simple way to treat that mathematically, so you can understand that, okay? That's, like I said, that's I would say is the best way of illustrate a solenoid. But don't forget, and this picture that you see right in here is exactly something similar to that. The only difference is that the core of the system in that illustration was a square, right? Instead of a circular donut. Instead of a circular donut was a square. And In order for you to either increase or decrease the voltage from the primary solenoid to the secondary solenoid, you have to adjust the number of windings, the number of turns in the secondary solenoid. Okay, let's see if we have another. Here you go, another one. See, the magnetic field is concentrated right here inside this metal donut, metallic donut. And because the area, the diameter of the solenoid ends up being equal to the diameter of the other solenoid, the magnetic flux through each of both solenoids, through each solenoid is going to be exactly the same one. Exactly the same one. Okay, let's see another one. Yeah, here you go. There's a real life solenoid that inside this carcass. And okay, here you go. That's another. Here's the core, right? Single, we call that a single phase solenoid. Three-phase solenoid because we have three windings here. Okay. Let's see another one. Okay, another one here. Okay, here is another type of induction device. This is called this is the donut shape, inductor. So here you go, picture of a solenoid. Let me copy and paste this one into my notes. Here you go. Picture. Picture of a real life solenoid as a transformer with made of two solenoids and a metallic core to concentrate the magnetic field. Okay? So let's write down here. Okay, transformer are electrical device that can change voltages in a rather straightforward and efficient way using the law of induction. Because it depends on the change of magnetic field, it works only with AC circuits. Okay? Transformers do not work with DC circuit. Why is that? That's because the law of induction relies on not changing current. Not changing current is slash B field. If a circuit does not change its current, then you cannot induce a current in the other in another circuit. Okay. Metallic core. Let's see. One way to create a transformer is to insert a solenoid inside another one, right? Just like you saw before. However, there is a more practical configuration that uses a metallic core to connect two different not different, but two separate solenoids, just like the figure above, just like the above figure. Okay, just like the figure above. Most transformers have solenoids of the same diameter and consequently same area. For this reason, the magnetic flux through the, let's say, the primary solenoid is equal to the magnetic flux of the secondary solenoid. And let's not forget the primary solenoid. Primary solenoid is the one connected to a generator, to a power source or generator. Whereas the secondary one does not need to be connected to a power source, since the primary is transferring its energy to the secondary one. And now we can start looking at the mass behind the transformer. Okay. It is because of this. It is because of this. It is because of the transformer that we can have a distant power station transmitting the energy, the electrical energy to your house, to our houses, right? To our houses. And okay, transmission of energy, of electrical energy, is done at a very high voltage, in order to lower the losses, the transmission losses. Transmission losses along the transmission lines. Once nearby, once next to your house, okay, the high voltage electricity is converted into a lower voltage electricity using a transformer. Okay, that was the reason that we ended up using alternate current. Okay, transformers. The fact that the higher voltages, high voltage, right? Let's put higher voltages can be transmitted along greater distances. Higher voltages, AC current, right? AC power can be transmitted along greater distances. Is the reason we use AC current today in our houses. There's a very interesting historical background behind that, okay? There is a very important and interesting background behind this fact, okay? back in the 1800s, in the late 1800s and early 1900s, comma, there was a fight between two camps, okay? And that was nicely dramatized in the movie The Current Wars. Do not know if you have watched that. If you haven't, make sure you Current Wars, right? The Current War, yeah, here you go, 2017 movie. That's the one. Okay, it tells the story of the conflict between Thomas Edison and Westinghouse, George Westinghouse. Thomas Edison was portrayed by Benedict Cumberbatch, you know, the Doctor Strange, right, of the Marvel Cinematic Universe. And they portray not just the fight between those two guys, but they also portray Nikola Tesla, who used to work for Thomas Edison, but then it didn't work out their work relationship, and later on Tesla associated himself with George Westinghouse. So what was the story? Okay, the story was that at that time, Thomas Edison was pushing for DC current to feed all the houses. He was pushing for a DC current infrastructure to provide current to all the houses, and that's that's real life. Okay, that's a real story. And Thomas Edison himself, he even ended up building more than one power stations that was providing direct current, DC current, to nearby houses. And then George Westinghouse and Tesla, they finally came to the realization that this, using direct current was not the right way of doing that, because this to provide direct current, you have to have a power station very close to the center that the power is going to be consumed. Okay, and then you're going to end up having several smaller power stations, which wouldn't be very efficient to do. So what they discovered is that instead of using DC current, by using AC current, it would be possible to build a very large power station very far away from the consumption centers and transmit the power through transmission lines at a very high voltage with very low losses along the cables. Okay? And that was the idea that eventually prevailed. Thomas Edison himself, he built more than one DC station to implement his idea. Thomas Edison himself was partial to this idea. Why is that? Because he had the patents for DC current, whereas George Westinghouse George Westinghouse and Tesla, right, had the patents for AC current. Eventually, we settled down with AC current, and all those power stations that Thomas Edison built were deactivated. And this movie, dramatized this whole story. It's a very interesting one. Okay. So one of the assistants of Thomas Edison was portrayed by the Spider-Man, right? Holland. This guy right in here. So that's the importance of transformers today. We have some videos on transformers. Let's take a look at this one here. Okay. Different transformer. Oh, here you go. We have one of this one here at LA Harbor. Okay, see the core? The core is connecting the two solenoids. Okay. And one solenoid has different number of turns compared to the other one. And what you have right in here is the power source, right, from the wall, which is AC current that's provided by a distant power station. And this guy here must be connected to a transformer to lower down or step down the voltage, otherwise it becomes too dangerous for us to to handle the voltage. Here you go. Here's another way of connecting two solenoids, right? Another way of making a transformer. Two solenoids with a metallic bar inserted into them. They have the same diameter. Consequently, the magnetic flux is the same through each of those two solenoids. Levers and gears of electricity. See the name that they gave it to transformers? The transformers is like it works just like a lever. Okay, by the same token that we can raise very high weights using a mechanical lever, transformers is something just like that. We can step down or step up the voltage using this device called transformer.
Transformers are everywhere, inside and outside of your home. They're in TV sets, sound systems, computers, and almost every electronic device. This thing is a very familiar transformer that is often used to provide lower voltages to electrical devices that cannot connect directly to the higher voltages of the wall. Also familiar are the transformers that look like trash cans.
Here you go. This is a transformer that we can see there in the streets, nearby your house.
High up on telephone poles. There's probably one near your school or neighborhood. These transformers are used to step down the voltage and correspondingly up the current to make it safer in the home. Understanding transformers involves knowing that currents can produce magnetic fields, and conversely, that changing magnetic fields can also generate currents. When I pass current, the compass will deflect. It's an electromagnet.
By the way, this guy that you see here, his name is James Lincoln, and he teaches nearby, in the Southern California area. I know this guy. He's very active with the physics community. Okay, and he's a very nice guy. He teaches high school physics there in Irvine.
Now we perform the reverse experiment. When I move this magnet through the coil, the galvanometer indicates that a current is flowing. Notice that when I hold the magnet still, no current is produced.
That's the law of electromagnetic induction, right?
The magnetic field must change in order to produce an electric field that motivates the charges. Note also the direction I move the magnet makes a difference. Michael Faraday was the first person to publish this discovery. It's usually known as Faraday. Now, the transformer puts both of these ideas together, but instead of using a bar magnet, it uses an electromagnet. When I turn on the power supply, it briefly produces a changing magnetic field in the first coil, and that produces a brief electric current in the second coil. Also, when I turn the power supply off, again there is a brief current, but in the other direction. This is the fundamental design of a transformer. Two coils that are connected magnetically but electrically separated constitute a transformer. The magnetic flux between the coils is greatly increased when a soft iron bar is added.
Here you go.
This improves the efficiency.
Here's the iron bar. It's very important because this iron bar concentrates the magnetic field generated by one of the coils.
Efficiency of the transformer by strengthening the field and preventing it from diverging out and being wasted.
See that?
Much better.
The deflection is much more intense, right? He still didn't connect these coils to the generator. Right now, he's just connecting the coil to a power supply that provides a very quick current change, right?
The transformers found in home appliances usually look like this. Here are the coils, which are wound on top of one another, and this surrounding structure is soft iron shaped to guide the magnetic field lines back around and through the coils. Typically, a transformer is supplied with an alternating current, since if the magnetic field does not change, the transformer would not work.
See what he's doing? He's changing the current in the power supply to emulate to emulate a generator. Okay, that's what a generator is. The generator is a device that have current that changes direction and change the magnitude and the flow and the direction of the flow of the current. Let's go back here. What he's doing here?
Typically, a transformer is supplied with an alternating current, since if the magnetic field does not change, the transformer would not work. Incorrectly using DC for the input of a transformer, like say a battery, might even damage it. The number of turns on an ideal transformer is in proportion to the voltage across those turns. Here, I have turns in an 8-to-1 ratio, and the voltage of 3 volts from my signal generator is stepped up by that same ratio.
Okay, so here goes. We have 200 turns in this coil, and we have 1600 turns in this coil. Because we have this ratio equal to 8, if we input 3 volts to this coil here, we are going to end up outputting 24 volts or 8 times more in this secondary coil. This one has the power, right? Has the power source. This one does not have the power source. And here you go. Look at the core, right? The core that he's using for this 2 transformers.
It should be 3 volts to 24 volts, but this is not an ideal transformer, and there are some losses, mostly due to flux leakage.
Okay, so there is some losses here. That's why you're not getting 24 here. That's what he's saying. Okay, but commercial transformers, they are very efficient devices. We are talking about 99% efficiency. This one is just for show and tell, right? Tell and show.
We need transformers because it's more efficient to send electricity at higher voltages. This is the symbol for a transformer, but here it's connected in an unusual way. There's a light bulb in series with the primary coil, which is connected to the power source, but also another light bulb connected to the secondary coil, which is powering it also. Here's the same setup in real life. As you can see, both bulbs glow. Now, what do you think will happen if I remove the bulb in the primary circuit? No real surprise there. I cut the power to the whole thing, like opening a switch. The next question is, what do you think will happen if I remove the bulb in the secondary circuit, but leave the bulb connected in the primary? Aha! Without the second bulb, there's an increase in impedance to the current flow. Impedance, Z, measured in ohms, is the ratio of the voltage.
Impedance is just the resistance in AC circuits. That is, that's the best way of understanding impedance. When you remove this light bulb from the circuit, what's going to happen? The resistance, the resulting resistance in the secondary circuit becomes infinite, very large. And because now the resistance is very large in the whole circuit, is going to affect the current in the whole thing. Okay, that's why the light bulb in the primary circuit went down as well.
Voltage drop across the device to the current that passes through it. This is very much like resistance, but it's a more general term that refers to all the elements of the circuit: inductor coils, capacitors, and resistors. We usually discuss transformers for stepping up and down voltages, but they should also be thought of as impedance matching devices. When the secondary circuit is open, there is no current to flow to oppose the changes in the primary circuit, and it experiences self-impedance. If you want to do this demonstration yourself, you must have an efficient transformer, and you should try to have the same wattage bulbs at their appropriate voltages in the primary and secondary circuit. For this purpose, we used an isolation transformer, that is, a transformer with a turn ratio of 1:1. It is convenient to alter.
Okay, he's talking about too much things right now. We can stop here, and I'm going to copy and paste in our notes links to those videos, okay? there is a second video that I'm not going to show you, but you can take a look at the other second video if you want to understand more about transformers, right? You can look at by yourself, and so here you go. Transformers can either step up or step down the AC voltage in an AC circuit. This is done by using different number of turns in each coil, right? So say we have 1,000 volts AC in a circuit. Don't forget the AC current is being generated by a generator. Okay. The AC current is being generated, is being provided by a generator. Okay. And what is the whole theory behind that? You just go back to Faraday's law of induction or electromagnetic induction, okay? Here you go. Our primary coil, okay, has a voltage that is related to the magnetic flux that flows through it times the number of turns in the coil. Okay? Think about that. The secondary coil is going to have a same relationship. Exactly the same relationship. Here you go. Secondary coil, number of turns in the secondary coil, and magnetic change in magnetic flux in the secondary coil. If the area, okay, if the areas of the two transformers are the same, okay, if the area of the two transformers are the same, comma, the magnetic flux is going to be the same too. Magnetic flux will be the same too, right? So we can write down like that. And then I'm going to, here you go, I don't need that. And I don't need that. And here you go. And I'm going to simplify my notation, okay? By dropping the subscript of both equations, okay? So now we have something like that. You know, here you go. I'm going to pass this term to the other side. I'm going to pass the negative sign to the other side as well, right? We got something similar for the secondary circuit. You go, secondary circuit. Let's not forget that the flux on the primary and magnetic flux on the primary and secondary circuits are the same. So I can write like that. I don't need this one. And now I can make this equation here equal to this equation right here, right? Since they are exactly the same, right? I'm gonna emphasize here by bold facing it. You go. They are the same, right? This one is going to be equal to the other one. Here you go. I'm just changing the subscript. I cancel out the negative sign. And I can here write the voltage in the secondary circuit alone. It's going to be like that. N sub S, N sub S divided by N sub P. Okay, and I'll just copy and paste this one here like that. Okay. And now we look at let's look at three different situations, right? Studying this equation, studying this equation carefully, right? Note that one, if N sub P is equal to N sub S, right? So we go. Then the voltage in the secondary is going to be equal to the voltage in the primary, right? Simple enough, right? Now, what if the voltage in the primary is greater than the voltage in the secondary? Let me move this one right in here. Oops. We just repeat the same procedure we had before, right? So here you go. It's going to be, if NP is greater than NS, now we are going to have that this number here is going to be a fraction of 1. It's going to be less than 1, right? Consequently, the voltage in the secondary is going to be less than the voltage in the primary. Also, if we have the opposite, that would be the case of a step down transformer. In this case, we have a step down transformer. And if it's all the way around, if NS is greater than NP, we have all the way around. We have a step up transformer. And then we have numerical examples, right? So we go real life examples. Those examples are just like real life examples. If the voltage in your primary is 240,000 volts, right? And you have a primary transformer that has 1,600 turns and a secondary transformer with 200 turns, what's going to be the voltage of the secondary transformer? Okay. The equation is, like that. Let's see. It's the ratio, right? That's the equation. Solution. Right? It's easy to remember, right? The ratio of the same device applies to the same device, right? Voltage in the primary divided by the number of turns in the primary is equal to the voltage in the secondary divided by the number of turns in the secondary. Another way to remember that is get the ratio of the voltage and the ratio of the number of turns. Vp is proportional to Np, right? So substituting 1600 on upstairs, right? And 200 downstairs, we have that the voltage in the secondary is going to be 8 times less than the voltage in the primary. So what does it mean? You know, if the primary is 240,000, right? We step down the voltage to 30,000. Let's put a comma here. Instead of 240,000, you're going to have only 30,000. What about the current, right? What about the current in the secondary circuit? What about the current in the secondary circuit? That's another example. We have to use the relationship for the power in the circuit. Okay, recall that the power is VI. If power gets conserved, and it's, and like I said, the transformers are very efficient devices, you can say that the power in the primary circuit is equal to the power in the secondary circuit. We can find out the current in the secondary circuit in terms of the current in the primary circuit. And he got, and instead of proportionality relation, we're going to have the inverse. The voltage increases, but the current goes down, right? And vice versa. So we are done with chapter 22. That's what we have for this chapter. Skip, let's see. That's all you have for this chapter here. And now we can start talking about the AC circuits. Chapter 23, AC circuits. It's 10:35 right now. Let's take attendance, and I think it is a good point to have our break. Let me take attendance, and we take our break, and 21st. Abir Ahmad, are you there? See. Hello, Abir, are you there? Okay, I can see a beer here, but I'm going to put a star under the name. Nestor Alvarado.
I'm here.
Okay, thank you, Nestor. And Monte Ambarshan. Monte. I don't see Monte here. Isabela Ballesteros.
Here.
Thank you. Justus. Is Justus here?
Oh, sorry, Professor. I'm here. My audio wasn't working.
Who is that?
I'm here.
I'm here. Okay, thank you. And what about Justus? Are you there? I see Justus here in my list. I'm gonna put a star under his name. Next is Alexandra. I don't see Alexandra. Oh, Justus. Okay, thank you, Justus. Okay, Alexandra. I don't see Alexandra here. Benjamin Carvajal. Thank you, Benjamin. Elizabeth Castellano. I don't see Elizabeth here. Next is Natalia Cordoba. Hello, Natalia. I don't hear from Natalia. Let's go for the next student, Jacqueline Delgadillo. Thank you, Jacqueline. Jenny Diaz.
Here.
Thank you, Jenny. Valerie Diaz.
Here.
Thank you. Juan Escalera. Escalera is, I see Juan. Oh, thank you, Juan. Bianca.
I'm here.
Thank you. Edwin Gonzalez. I thought that Edwin was here. No, doesn't look like. Okay, next is Eli Gonzalez.
Here, Professor.
Thank you. Manuel Hernandez. Thank you, Manuel. Samantha Hubert. I don't see Samantha here. Joseph. CJ Joseph Houghton. CJ, I don't see CJ here. Amber Lopez. Thank you. Arely Lopez. I don't see Arely here. Okay, next one is Genesis Lopez.
I'm here.
Thank you. Mary Michaelian.
Here.
Thank you, Mary. Galia. Galia Odabashian. That doesn't look like. Ramon Olivares.
Here.
Next is Taylor Forn. Doesn't look like he's here. Jeremy Pittman. No. And Stephanie Ramos.
I'm here.
Okay, thank you. Next is Leslie Rios. Thank you. Jason Strait.
I'm here, Professor.
Thank you. Next is Hema Torres Navarro. Doesn't look like Hema is here. Let's see how is. $19, $21. Let's see. We have just one. Natalia, are you there, Natalia? Okay, Natalia is not answering, so let's go for our break. Okay, break. 10:41 to 10. 56 a.m., right? I see you in 15 minutes. I am back here. And now we're going to talk about AC circuits. Okay, AC circuits is more difficult than the DC circuits, okay? DC circuits is much simpler because the current and the voltage is constant. But then when we start to get the current to change, when the voltages start to change, then we are going to have some things that has a different behavior, okay? So here go, two different types of circuits. DC circuit and AC circuits. Okay, so just like I said before, right? Let me put the drawing here for you. Here you go. Here's an example of the simplest AC circuit that you're going to find out there. Is the circuit with a resistor, the AC circuit with a resistor. Just like we have a DC circuit with a resistor, we also have an AC circuit with a resistor. And I'm going to do here you go. And the current in the circuit flows back and forth, back and forth. That's why I have this sinusoidal symbol right in here. Okay, the generator whose voltage changes as time goes by, changes sinusoidally. Okay, here is another type of AC circuit that you're going to see. A little bit more complicated. Instead of a resistor, you have a capacitor there. And capacitor behaves differently in a AC circuit if compared with the DC circuit, okay? And then here you go. The third, remember that? Capacitor, resistor, and then we have the other circuit that has an inductor. The three basic elements in electricity and electronics. Okay? At this instant of time, the generator has this polarity here, and the current is flowing in a counterclockwise direction, not just for this circuit here with an inductor, but also for the circuit with the capacitor and the resistor, okay? And let's talk about, we're gonna cover the circuit with the resistor first, because it's the easiest one to understand. But before we go into that, let me just put a table in my notes. Here you go. Direction of flow of the current is one direction only, either clockwise or counterclockwise. Here, the current in the circuit is in both directions, depending on the instant of time. Okay. The power source for a DC circuit is a battery. The power source for an AC circuit is a generator. Voltage is constant for DC circuit. Voltage varies sinusoidally. And I'm gonna lay down all the basic circuits the basic types of AC circuits that you have there. The simplest one, that's the easiest one to understand, is the one with a resistor only. Easiest one to understand. Easiest one to understand. Then you have just like I mentioned, an AC circuit with a capacitor only, with an inductor only, and then a combination of the above elements. You can have a circuit with a resistor and a capacitor, a resistor and an inductor, a capacitor and an inductor, and all the three circuits together, put together, resistor, capacitance, capacitor, and inductor. Okay. So let's talk about a circuit with a resistor, AC circuit with a resistor only. And let's take a look at this simulation here. Let's see. We have a nice website that you can build circuits, and that's the FET. Let's take a look, not motion, not sound, let's see, electricity. Just electricity, nothing else. Okay, here with this, in this website, we can build all sorts of circuits, okay? All sorts of DC and AC circuits. So that's the next thing, the next best thing to do the actual experiment is to do a simulation. So let's see what we can get here for let's see, this one maybe circuit AC, this one. Circuit construction kit, see that? AC. And we have our AC circuit, RLC, Kirchhoff. Let's try this one here. See what's going on here. Why is that? It's not related CM. For some reason, it's not working here. It looks like we are. Let's see if this one works. Yeah, this one works, but that's not the one I want. Let's see what's going on this website. Let's see here. Maybe, yeah, okay. Looks like we got it now. AC voltage. Let's look at this one. Yeah, okay. Here, what we are going to do, we are going to put together a circuit. Here you go. The AC generator, right? The AC power source. And here's the wires that we connect the circuit. Like I said, better than that, just having the actual circuit with wires for you to put together, okay? So here, guys, what I'm going to do, I'm going to put together an AC circuit with a resistor only. We also have switches here, okay? Here you go. I can close the switch, I can open the switch. Just like the switch that you have there at home to turn on and off your light. And now I'm going to put a resistor. Here you go. Do you see the bands of the resistor here? Wire. And now we're going to close the circuit. Close it, close it, close it, close it. Here you go. And now, here you go. Look at the charges, the negative charges here in the circuit. They have the blue little charges. I'm going to close the circuit. Look what happens to the charges. They move back and forth. There's a very good picture of what happens microscopically to this circuit. Let's see, I'm going to increase the frequency of my generator. Okay, it's possible to do that. And then what's going to happen? The charge is going to oscillate faster. If I increase the voltage, the amplitude of the charges is going to be larger too. See that? Lower voltage, lower amplitude of oscillation. Higher voltage, higher amplitude of oscillation. And now we can come up with the voltage chart. I can connect this This is like a multimeter, but it's a fancier multimeter. We call it an oscilloscope. Okay, this oscilloscope, this device, this multimeter, can plot the variation of the voltage as time goes by, and that's what you have here. And let me decrease. Let's see. I'm going to. Let's see, out of range. Let's see. Yeah, I am zooming out. Okay, so here you go. See the voltage, how it varies as time goes by. Let's see, we can adjust the frequency, we can adjust the voltage, right, of the circuit. Let's adjust the voltage instead of 1.49 hertz. Let's decrease to 0.62. Now the period is longer, right? Lower frequency, higher period, longer period. Shorter frequency, higher period. And can adjust the voltage as well. Look at, I'm gonna decrease the oscillation of the amplitude of the circuit. Okay, that's what a generator does to your circuit whenever you have a voltage, whenever you have a generator. Okay, we have the link. If you want to play with that, it's a good idea to play with it. And you can come up with different, right? Different types of circuits. We can put a capacitor here as well, okay? But let's start with the simplest of all circuits. Okay? Mathematically speaking, how do we treat this circuit mathematically? Okay, we start with the generator. The generator is generating this voltage here that you see that changes as time goes by. There in the simulation, I was able to change the amplitude of the circuit and also the frequency too, right? I was changing the frequency as well, which can be here written as angular frequency omega. 2 pi f is the angular frequency. That you got, oh, no, not this one. I want this one here. That's the relationship between the frequency and the angular frequency. Okay. What's the difference between them? Well, one measures the frequency in number of oscillators per unit of time, and the other is the radians per unit of time. It's kind of is the angle, right? That's why we call it radian per unit of time. When you have a resistor in the circuit, we can find out what is going to be the current in the circuit as well. And we do that by using Ohm's law, right? Here you go. Ohm's law is R times I. Ohm's law applies to an AC circuit. And since the voltage is a function of time and the resistor is constant, what's going to be a function of time is going to be the current, right? Like that. And we can here write the current as a function of time. V naught over R sine 2 pi ft. Okay, what you have to note, see, I'm going to put the current and the voltage side by side. Here you go. Current and the voltage side by side. Not side by side, but one on the top of the other, right? Here you go. And I'm going to put the function of time here as well. Note, see that they have the same argument. The sign has the same argument. They have very similar relationships, right? They are both directly proportional to the sine of 2 pi ft. They are both proportional to that. We don't say the same for the other types of circuits. Okay? That's why I say that the AC circuit with a resistor is the simplest one that you're going to see out there. We say that both the voltage and current are in phase. Okay, are in phase when we have this type of relationship. The same argument. Okay. They both have the same argument in the sine function. They are in phase. I'm emphasizing that because we do not have something like that when we input, okay? When we put a capacitor or an inductor to the circuit. Something like that does not happen whenever we insert an inductor or a capacitor in the place of the resistor. Okay. And I'm going to write that down here, the relationship. But before we go into the capacitor and the inductor, I'm going to show you a very nice way of displaying another different way, right? A different way of displaying the voltage and the current in the circuit. So here you go. Here is the AC circuit with the resistor. Okay. Here you go. The voltage can also be displayed in a graphical sense. The above equations for the voltage and current can be displayed alternatively and graphically in the following way. This type of diagram is called the phasor diagram. Okay, so what we have here, we have a vector. Okay, this vector represents the amplitude of the voltage. That's why I put V naught here. And this vector makes an angle 2 pi ft with the angle, with the axis x. And this vector is rotating as time goes by. The projection of this vector along the y-axis is the actual voltage. You see that? Here you go. This V that you see here corresponds to the projection of the vector in the y-axis. V naught is going to be the whole vector length. And 2 pi ft is going to be the angle, which is exactly the argument in the sine, inside the sine function. Okay? So you can picture this thing rotating as time goes by. That's what a phasor diagram is. A very useful type of diagram, allows you to solve problems more quickly, okay? And note that we have the same thing. We can do the same thing for the current. We can have the same phasor diagram for the current. And I'm putting that as a different color, right? Going back I'm gonna put them here. That's the V, right? The V of T is this projection here. And we have the same here for the current as well. We say again, we say that the current is in phase with the voltage, which is not the same that happens for the AC circuit as a capacitor and inductor. We can superimpose both of them in the same graph. And it's gonna look like the following. It's gonna look like that. They all rotating in the XY space. And now we're going to replace the resistor with a capacitor. Okay? That's gonna be our second example. Replace the resistor with a capacitor or capacitance C. Use Kirchhoff's loop law to find the equation for this new AC circuit. And by the way, that's how I obtained this relationship that you see right in here by using Kirchhoff loop law. Okay? That's how you obtain it. You go ahead, you start at this point, you cross the generator, you get V naught sine 2 pi ft, goes through the resistor. We're going from positive to negative at this instant of time. Consequently, we have minus VR, right? Let's do that. Let's do that. I didn't do that before. Let's do that using Kirchhoff loop law, okay? Using Kirchhoff's loop law, we obtain the following equation for this circuit. We have just one loop, so it's going to be easy, right? So first we have to go through the generator, and here you go, voltage of the generator, right? Minus the voltage through the resistor. We have a negative sign because at this instant of time, we're going from a region of higher potential to a region of smaller potential. We close the loop. Consequently, what we have at the other side is going to be 0. But for the generator, you already know that the generator behaves just like that, right? I can replace the VG with V naught sine whatever. And we can replace the V sub R with the resistance times I, and I'm not gonna put the time dependence. And here you go, finally, we have this relationship here, right? And we can do the same for the capacitor. That's the key to solve circuits to solve problems, right? Of AC circuit. And here you go. We do the drawing again. AC circuit with a capacitor. I'm replacing the resistance that was here with a capacitor. Current is flowing at this instant of time, is flowing counterclockwise. I choose the loop direction as being counterclockwise as well. Because the current is flowing counterclockwise, this plate of the capacitor is going to be at this instant of time positively charged, right? The flow of the current corresponds to the flow of the positive electric charges. And consequently, this other side of the capacitor is going to be negative. And then, just like before, using the Kirchhoff loop law, we have the following relation. V through the generator minus V through the capacitor. Going from positive to negative, equal to 0. And then, just like before, we substitute the V of the generator, right? Here you go. By that relationship that I mentioned to you, here you go. V of G is equal to V naught sine 2 pi half T. And then what about the V of the capacitor? Okay, the V of the capacitor, we use exactly the definition of capacitors. Do you remember the definition of capacitors? It is going to be T is the charge divided by the V of the capacitor. Okay, and then we solve for the V of the capacitor and plugging in the equation above. Something like that. Okay, and now substituting both equations into this other equation, we're going to get something like that, right? And which will become something like that. Which becomes something like that, okay? Or, here you go. I can even write that down. Even write Q as being V naught over C. Oh, sorry, not V naught over C, V naught times C. Like that. That's the charge. That's how the charge varies. It's not like how the current varies. The current is gonna vary in a different way. The current is gonna vary in a different way, right? So remember that the current is going to be given by delta Q, right? Over delta T. Delta T. And delta Q over delta T is something like the following. Like this one here. Okay? Because we have C and V naught are constants in time, they can be taken out this delta T. And, if you took calculus, okay? If you took calculus, when you take this type of ratio here, what you end up getting is going to be a cosine of 2 pi ft, right? Times 2 pi f. Don't have to take calculus to understand that, but you have to memorize this result that you see right here. And now take a look what's happening here. The current is no longer proportional to a sine. It's proportional to a cosine. And this cosine can be rewritten in terms of a sine, right? This cosine can be rewritten in terms of a sine, which is sine plus pi over 2. Right? And now I can replace, I'm going to replace here. Here you go, 2 pi ft plus pi over 2. And then we go back to the voltage of our generator. Okay, note see, no, the argument is different. The sign function is the same, but the argument is different. Okay, and let's go back to the charge, right? Here you go. The charge is this one, going back to the generator, right? The charge, the charge is in phase with the voltage because the argument of the sign is the same, but not the current. The current is not in phase with the voltage. Okay, so looking at the above, okay, we note that the charge in the capacitor is in phase with the voltage of the generator. However, the same cannot be said of the current. Okay, we say, the current is out of phase with the voltage by 90 degrees. By 90 degrees. We also say that the current of the capacitor of the current of the circuit, right, leads the voltage by 90 degrees. Okay. Leads, right? Leads because you have at 90 degrees, you have positive sign, 90 degrees. And in terms of, and let me do one more step here. Okay, one more thing that you have to note is that the amplitude of your current depends on the frequency. So you can increase or decrease the current just by changing the frequency in your system. Okay, you can increase and decrease, and let's do that in the simulation. Here you go. I'm gonna get rid of this guy. Let's see. Cut it. Cut it. Let's see if I can get a capacitor here. Now I'm gonna put a capacitor. Do we have a capacitor here? Oh, this doesn't look like we have a capacitor, unfortunately. Battery voltage. Yeah, we don't have a capacitor. Let's see if you have in another simulation. Shit. Huh. RLC. Okay, this one here. Maybe, let's see. Let's see if we have a, yeah, we have an inductor. Yeah, we have a capacitor here. Let's build our circuit. But first, let's start with our generator. Wire. Wire. And we need the switch. Switch, wire, and a capacitor. Okay. Wire. And now you're gonna close the circuit. Like that. Okay. We close the circuit, and just like before, here you go. You're going to have those charges oscillating back and forth. Look at the charge buildup here, right? Red is positive, blue is negative. Okay? Look at the charge buildup in the capacitor. Now I'm going to use an actual voltmeter. Okay, here you go. Here you go. The voltage is oscillating back and forth. That's what you would see in real life. Or you can also measure the instantaneous voltage with this guy here. So here you go. And you also have another device that measures the current. See that the current chart? Let's see how I'm gonna do that. Oh yeah, here you go. The current right here. Let's move away. Yeah. Let's see if we can pause momentarily. Oh yeah, we can pause here momentarily. Right in here. Look at the beginning of the current. The beginning of the current, we have a maximum current, but the voltage is at a value of 0 volts. See that? That's what we call that the current leads the voltage by 90 degrees. The voltage would be somewhere around here in this graph, okay? A 0 value, and the current is ahead of the voltage by 90 degrees. That's exactly what we see in real life. Okay, so let it flow. And also note that the amplitude of the current changes with the frequency as well. If we increase the voltage or the frequency, what's going to happen to the here you go. We should see an increase. Let's see if they did. Yeah, they did implement that. They increase the current, increase the amplitude, right? And I'm gonna pause momentarily here. So this simulation is realistic. And now I'm going to decrease the frequency. And this amplitude of the current should decrease as well. See that? Here you go. The amplitude, see that? Much lower, right? Let's see how far I can go here without, yeah. The amplitude is clearly lower. The amplitude for the lower frequency is lower than the amplitude of the current for a higher frequency. Okay? So here you go. The current is out of phase. Furthermore, note, see that the amplitude of the current is a function of the frequency of the generator. It increases, right? It increases. That's what I call my I naught. I'm going to write that down here. I naught. I naught is equal to that. There you go. In terms of a phasor diagram, what's that we have? We have this type of phasor diagram here. V naught makes an angle of 2 pi ft. It's the phasor is rotating in a counterclockwise direction. The charge is going to be in phase with the voltage, right? 2 pi ft, but not the current. The current is going to be leading by an angle of 90 degrees. Omega t plus 90 degrees. Let's see if I can put the, yeah. And now I can combine all those three phasors into a single diagram like that. This one is for the charge, the red is for the voltage, and the blue is for the current. There is a 90-degree angle between those two. Can you remember that? Okay. With the capacitor, with the capacitor in an AC circuit, a capacitor in an AC circuit, comma, the current leads the voltage by 90 degrees, or the voltage lags the current, right? Either way, by 90 degrees. Either way is correct. What's next, right? Okay, one more thing. Recall Ohm's law, right? Ohm's law is what? V equal to Ri. Man, this pilot here gets in the way. V equal to Ri, right? V equal to Ri, which can also be here written, right? As there's another way of writing it, is I equal to V over R, right? And then we are going to rewrite our current in this exact format. The current is inversely proportional to the resistance, right? We're going to rewrite our AC, the expression of our AC current in a similar way. And I need to get the other one, this one here. This one that I need. Okay, so what I want is this one right here. Okay, so here you go. Let's take a look. I even gonna put, to make things easier to visualize, I'm gonna put V naught here and I naught here, okay? And then I'm gonna write that down. I naught here and V naught here. Let's not forget that I naught is this term right here. The amplitude. I naught is mean the amplitude. Okay? But then notice that we have a V naught term here. I'm going to isolate this V naught here in this equation. And I'm going to rewrite this whole equation here as though as I am dividing V naught by a term, which, by the way, must be, okay, like that. But it's not, this equation is not the same as this one, right? But I can rewrite that as being 1 divided by that. That would be the same, right? That would be the same. Here you go. Right? And now compare, we have V naught here, we have V naught here, right? This whole term here is I naught. But this term here is going to have the same unit as the resistance. And that's what I would call this term here, I would call the AC resistance term, okay? Note C that the term downstairs has the same unit of resistance. Okay, and the term like that. This guy right in here, I'm going to put a square bracket. Square bracket right in here has unit of omega, unit of resistance. So this term that you see here, we call it, because of that, we call this term the impedance or the AC, right? I prefer to call it the AC resistance. Oh, sorry, it's not impedance. We call it the capacitive reactance or the AC resistance. Capacitive reactance, right? Capacitive from the fact that we have a capacitor here. Reactance should be the resistance, the term that we use for the resistance. We use the following symbol. Most books use the following symbol for this capacitive reactance. The letter chi. The letter chi with the subscript. Okay, and now we can rewrite and the current for a AC circuit with a capacitor. Yeah. We write like that. V naught over chi C. And then we have, we can start building up our equations, right? So we have the current for a resistance in the circuit. We have the current for the capacitor in the circuit. But don't forget, what you see right in here is just a relative phase, okay? The phase, remember that the phase you see above is relative to its corresponding voltage. Okay? So it's not enough to write like this way. We have to also write down the voltage of the generator. This one right in here. In both cases, right? I'm gonna put the voltage in between here. Like that. This one leads the voltage. This one is in phase with the voltage. The phase term you see above is relative to its corresponding voltage. And now we have the third example. I think we should go for a break, right? Well, the third example is going to be of the inductor. Let me just set up this example for you. Okay, so here we go. Our third circuit, replace the capacitor with an inductor. The inductor is just like a coil. And we gotta use Kirchhoff's loop law to find an equation for this new AC circuit. Let's set this one up. Okay, so here we go. We go around the circuit. Now we are going to have we're increasing voltage, right? And then we have a voltage across this inductor as well. I'm gonna put it as a positive sign for now, but in reality, it's not a positive sign. You know, just remember that there is that relation for the Faraday's law that involves an inductor. Okay, remember that? Here you go. It's minus L delta I over delta T. And when we substitute both for the voltage, for both voltages, right? In the equation, here you go. We get something like that. 1149, let's go one more step and then we worry about our break. Here you go. We have this relation here for the inductor. And now the solution for that is different from the for the capacitor. The solution for that, I'm gonna just give you the solution. You have to memorize that, okay? It lags. The current lags the voltage. Okay? That's why we have this negative sign here in the phase. Negative sign in the phase. Negative sign in the phase means that the current lags the voltage. Okay? So the symbols like that, you know, it's not difficult to memorize that. Capacitor is the easiest, simplest device you have out there, right? Resistor and the inductor. That's in order of difficulty. Okay. Capacitor, current in the capacitor, current in the capacitor lags in the resistor is in phase. No, sorry. Current in the capacitor leads, sorry, is in phase. In the inductor lags. Can you remember that? So that's an easy way to remember. Capacitor is the simplest device that you're going to see out there. and it's already 11:51. Let's take our break, right? 11:51. Let's see. Yeah, 11:51, 12:06 p.m. Any questions about that? We're talking about the current, right? But when we talk about the voltage, right? It's all the way around. Voltage for a voltage capacitor lags, current lags. Okay, lags. I'm gonna put it this way: 1, 2, 3. The voltage, right? Voltage for an AC, it would be better circuit with a capacitor, right? Current for an AC circuit with a capacitor. For an AC circuit with a capacitor leads the voltage with a capacitor. Now, voltage for an AC circuit with a capacitor lags, is in phase, leads the current. Leads the current. If we put in this way, it becomes easier to remember, right? Leads the current. Did I put oh, I didn't. Okay, we should have, let's go for 2 more minutes. Let me see if I have here, here you go. I have here the phasor diagram. Okay. Here you go. So now we have a phasor diagram. Here you go. Here's the phasor for the voltage. Here's the phasor for the current that lags the voltage. And then here's the phasor for delta I over delta T. It's displaced by 180 degrees. That's why we have that minus sign, okay? The 180 degrees stands for the minus sign. Let's go back there. Here the minus sign. Let me see, yeah, the minus sign here, okay? That shows that there is a lagging 180 degrees. And now we can go back to we can start our break, right? 11. So any questions? I see you in 15 minutes. Bye-bye. I'm back here. And there is a mistake here, folks, in this drawing here. I got a little bit confused with this thing, but it's obvious from the equation. Here you go. What do we have here, right? We have a minus sign here, and when we pass this term to the right side, we end up with a positive sign, right? And let's do another step here. We get delta I over delta T is V naught over L. Okay, and then obviously from this relation that you see here, there's no negative sign, right? So what does it mean? It means that delta I over delta T is in phase with the voltage. Okay, let's get the VG again. put it just below the delta I, delta T, Pg. Right here is in phase. So when we do the phasor diagram, this diagram is also needs to be fixed. So here go. Delta, that's the one we want. Let's fix that. And snipping tool. Actually, it shouldn't be delta. Delta I should be only, here you go. Let me fix that. That's also delta I over delta T is this component, okay? This component here is delta I over delta T. And this whole thing that you see, the whole vector, you have to look back at our equation. This one here, delta I over delta T, yeah, okay, V naught over L, okay? V naught over L. The whole vector is V naught over L. V naught over L. Fix that in real time. And I'm gonna put with the same, everything with the same color here, so it will not mix up. Right in here. Okay. The projection, that's delta I over delta T. The whole vector is V naught over L. Okay, so I'm going to replace that right in here. Here you go. That's the right way. The current lags, okay, and so we have all the elements here that we need to go to the next step. Okay, and this one is going to be the voltage. And now we can display everything at once. What I want to do is to put the current of the capacitor before the current of the resistor. We started with the resistor because the resistor was the easier problem to solve. But don't forget, the simpler element is not the resistor. The simpler element is the capacitor. Right, so here you go. Capacitor leads, resistor is in phase, current of the inductor is lag. Current of the inductor lags. Okay. Leads. Huh? Leads. In phase. In phase. Lags. lags. But then I'm gonna remember, now suppose that that's not the correct way of saying that, okay? Because I'm gonna explain that to you. First, let's take a look at the system. That, that what we say, the above is what we say with respect to the voltage, right? But with respect to the current, we say otherwise, right? Otherwise. We say otherwise, or so given. So in other words, if we consider the current as being the reference, right? Suppose that we have a relation like that. The current I naught sine of 2 pi ft, we would say that the respective voltage for a capacitor only, right, lags the current. Lags the current. It's all the way around, right? Because I inverted the reference. For a resistor that's going to be in phase, and for an inductor, the voltage leads. The voltage leads, right? Let's see if we have everything right here. Lags, in phase, and leads. Yeah, everything is. Actually, that's exactly the correct way of thinking in terms of lagging and leading. I'm going to tell you why. This reference is the correct one. Is the right one to think. Is the right one to think for a very important reason, right? Is the right one to think about, okay? For a very important reason. Is the correct one. This reference is the correct one. The right one to think about for a very important reason. Consider, for instance, a more difficult, a more generic, for instance, a different circuit. One that involves all the three elements: the resistor, the capacitor, and the inductor. Okay, and I'm going to display here for you this circuit. Let's see here. Oh, right in here. This one right in here. Here you go. Resistor, inductor, and capacitor. Okay. In this type of circuit, in this type of circuit, you cannot have a discontinuity in the current. You cannot have a discontinuity in the current through each element. In other words, the phase of the current through the resistor must be the same through the inductor and the capacitor, okay? Remember, we are looking at a specifically spot here. So we cannot have a discontinuity in the current when the current enters the inductor. Okay, so the phase must be the same just before entering the inductor. That you cannot have a 90-degree phase shift. For this reason, we must always think of the phase difference in terms of the current. Okay? The discontinuity instead is in terms of the voltage. So in this specific circuit now, we are going to have for an RLC circuit, we have the following relations. Okay. Well, using the Kirchhoff law, right? So consider that as though as an example. Let's try it. Let's treat that as though as an example. Here you go. Just like we did before. Example 4. Now consider RLC AC circuit with known RCL and frequency values, right? Values. Use the Kirchhoff loop law to find an equation for this new AC circuit. Use the phasor diagram to find the net voltage of the circuit. Write the current for the circuit and use the phasor diagram to find the phase difference between the current and the voltage. This problem is a little bit more difficult, okay? So let's look at this item A first. Just like before, we have a single loop, right? And when you have to go through the whole loop to get the equation of the voltage using the Kirchhoff loop law, item A. And that's going to be at this very moment that you're going to understand the power of the phasor diagram. Using the Kirchhoff loop law, you're going to have voltage through a generator. We're going to have a decay in the voltage through a resistor. Okay, we do not know what's going to be the sign of the voltage through the inductor. Faraday's law is going to tell us, but we do know that the sign of the voltage across the capacitor must be negative if the circuit, if the generator has this polarity at this very moment, right? If the polarity here on the right side is positive, it means that the capacitor is going to have a positive sign on display and a negative sign in display. Since you are going from the positive voltage to the negative voltage, we must have a negative sign right in here. Okay? So we repeat exactly what we did before. In order to get to this type of circuit that's the most generic one, we have to study what happens to each element separately. Okay? That's why we did just for the resistor, just for the capacitor, and just for the inductor. And that's item A here. we go substituting for VG for the voltage of the generator, right? We go. I'm going to erase it here. For the voltage of the resistor, we use Ohm's law. Okay. For the voltage of the capacitor, we use the definition of capacitance. And then, ideally, we should put here this one at the top, right? So you can see the natural progression, charge, current, and the delta I over delta T. Okay? And there is this negative sign. Okay. And now, so we substitute all the relations that you see right in here. Okay. Even better, I'm gonna put this term. I'll keep it like that. You know, because all elements in the circuit are in series, okay, then the current through all of them must be the same. At a given instant of time, the current through the resistor must be equal to the current through the inductor and equal to the current just before and just after the capacitor. That's what I mean by having a continuity, but I mean having a continuity in time. Okay. And how do I display that mathematically? The current through the resistor must be equal to the current through the inductor, and the change in the charge in the capacitor as a function of time, okay, which I call the current of the capacitor. Everything must be equal to I. And then we can rewrite our equations by dropping the subscripts. Okay. Dropping every subscript. And now I rewrite the current as the reference of my circuit. Something like that. And here is the term of the resistance, right? The impedance. The impedance. The RLC resistance. Or even better, the AC resistance. The currents are in phase in this RLC, okay? The currents, here you go, that's right. The current is in phase through every element in the RLC circuit, but not the voltage. Okay? The voltage through are not necessarily, but not necessarily the voltage. Let's put it this way, not necessarily the voltage. It is in phase for the voltage across the resistor, yes, but not for the capacitor and the inductor. In the case of the capacitor, you know, the voltage is gonna lag. In the case of the inductor, the voltage is gonna lead. I'm just repeating what I said before. Okay? Now we go back to our phasor diagram to find the final relation for the voltage and the current. And that's gonna be item number B, item B, okay? Item B is gonna be like that. That's where we combine, all the elements that we found before, okay? So here you go. That's the phasor diagram that we have for the RLC circuit. Phasor diagram of a RLC circuit. Okay. The voltage across the resistor is going to be in phase with the current in the circuit. The voltage of the inductor is gonna lead, right? Let's see if it's leading. Making sure everything that I said there matches what I have here, right? The voltage, the circuit with the inductor leads the current, right? And then I put the V sub L. Shouldn't be V sub L because it must be the amplitude, right? Here should be the amplitude. V sub L is what's projected here. And the V of the capacitor should lag the current. And the net voltage in our RLC circuit is going to be the vectorial summation of everything that you see here. The net voltage in a RLC circuit should be the vectorial summation of all voltage phasors. Okay, and I'm going to do that in the phasor diagram first, and then we worry about the equations. VC is going to subtract from the VL. There is a 180-degree phase difference between those two voltages, right? So here you go. And then I'm calling that VLC, VL minus VC. I'm assuming that VL is greater than VC. Assuming that VL is greater than VC. Subscript and the subscript. And now we have to sum those two vectors that are 90-degree. They are all rotating omega t. They all have the same angular velocity. Okay, here you go. That's the next diagram that you have to worry. RLC, here you go. VL minus VC and VR. Summing VLC with VR. We get, something like that. Final VRLC phasor. There is an angle phi between the current and the resulting VRLC. Okay, and now we can do the math. Okay, let's do the math. The math is going to look just like that. Here you go. The voltage VRLC is the square root is this one here that I'm doing, right? 90-degree angle, so we use the right angle triangle formula, which is the VLC square plus VR square. But let's not forget that VLC is one minus the other, VL minus VC, or VC minus VL. Okay? And VC minus VL is given in terms of the capacitive reactance and the other term that we write like it is in the Ohm's law. Okay? So here go, we're going to write that down in terms of the current. And now we have the impedance that I'm going to call the Z. Okay, I'm taking out the I square from this square root. Here's the resistance. Those two terms, you know, they are just the AC corresponding of the resistance for an inductor and a capacitor. And that's item B, right? Item B that we asked for. Use a phasor diagram to find the net voltage of the circuit, VRLC. And item C. Now we have to find what's item C? Item C is write the current I for this circuit. Okay, just by looking at the diagram of the phasor diagram that you drew, right? Just looking at the, if VL is greater, here you go, item C. It's going to be something like that. V naught Z sine 2 pi ft. The current, you know, according to this drawing that you see here, you can see that the current lags the voltage by an angle phi. Later on, we're going to find out what this angle phi is all about. So that's why I put the lagging factor here, minus. Okay, and that would represent, you know, that would be for the case in which VL is greater than VC. If it were the contrary, right, we would have a different sign there for the phase angle. VL was less than VC, then we would end up having this sign instead. And finally, we can find what is this angle phi. What is going to be this angle phi? Let's take a look. You know, don't forget that we have VL minus VC here, and we have VR here. Okay, so what you're going to have is going to be a tangent of phi. Tangent of phi is going to be the length. Let's see, here you go. Here you go. Phi angle is this one right in here. Right? The tangent of phi is going to be what? This length here divided by this length here. And we can write it down. Item D. Let me see. Item D. That length that you saw before. Okay, we can here write the term that we have here. And you can invert phi, right? The phi is going to be the arc tangent of this. Oops. the arctangent of this term. What time is that? 12:41. The power, okay? Now, okay, so that's we're done with this example, right? Where the angle phi is obtained from the phasor diagram as being something like that. And then, we can even invert this thing here. Here you go. I didn't invert yet, but we can invert it. Now I'm going to put that inside a parenthesis, arc tangent, and the phi angle, like that. What's next? We have 7 more minutes to go. Now let's talk about the power of an AC circuit. An AC circuit. Recall that the power in a DC circuit, right, is given by, don't forget, we obtained that from Ohm's law. Ohm's law and the definition and the energy in the circuit. Potential, and more specifically, the potential energy in the circuit. Here you go. VI RI square. Okay. In the case of a DC circuit, this power is constant because B does not vary. Okay. However, for an AC, the instantaneous power, right? Let's put the instantaneous power is constant because it does not vary in time. However, for an AC circuit, the instantaneous power must vary because B varies in time. V and I vary in time. Okay. For this reason, we must define an average power, but it must be a special type of average for the following reason. Okay? And that's going to become easy to understand if you consider that the sine function, right, spends the same time on the top as a positive value as well as a negative value, right? Notice that the voltage is a sine function. So the sine function spends some time, half of the cycle in the positive region and half of the same cycle in the negative region, right? If we take, you know, here you go. If we take the regular average of the above function, comma, we'll get a value equal to 0. So this, for this reason, this average is not very useful. It's not very useful. For this reason, we must define a special type of average. Special type of average. Okay, that we call the root mean square value. Okay, root mean square value. And what is this root mean square value? There is the square root of the average of the square, okay? Of the square. The square root of the average of the square. First, in this special type of average, comma, first we square the original value to eliminate the negative from the equation. Then, in this special type of average, we do the following, okay? Let me walk you step by step. One more minute to go. We do the following. First, we square the original value to eliminate the negatives from the equation. Next, we take the average of this squared value. Finally, we take the square root of this average. Okay, that's the special root mean square value. So this special type of average is called the root mean square value. It's 12:50 right now. I think it is a good point to stop here. And I'm gonna have office hours right now. If you want to hang around to talk to me, I'll be here. Okay, and we'll have an exam on Wednesday, right? So I see you the day after tomorrow. Welcome, Natalia. Thank you.
Thank you, Professor. Goodbye.
Goodbye.
Thank you, Professor.
Welcome. Bye-bye.
Thank you,
Next.
Professor.
Welcome.
Hey, Professor.
Hello, Edwin.
Just wanted to let you know that I was here. I was having some problems getting in. That's the reason I came in late.
Okay, so let me see. Let me stop the recording first.